test.
Okay. So what happened to the battery now? Oh, I see. Is it anything I can destroy by doing something, pressing buttons? Okay. So this is here. Cannot, oh, okay.
It's good.
All right, done. Thank you. Thank you. All right, so thank you very much for coming here. I hope I will tell you something which you didn't know before, but you will find something among many transparencies which I want to show. This is going a little bit against what was told yesterday. That first we look at the data, and then we build a theory to explain the data. In this case, we have first built a theory and then found out that it actually explains a lot of data. So first we found the medicine, and then we found the illnesses for it. But the secret of all this is that the theory is built on basically on Navier-Stokes equation, which includes a lot of data from many different times and many different researchers. And what we did, we tried to extract information from this equation using purely mathematical tools. And in this sense, what we developed is, we can call it even kind of Ariadne thread for people who are wandering in the labyrinth and trying to see what way is the most productive way to go. So sometimes building an analytical theory is actually very useful for guiding data analysis and for different theories which are built to explain the data. The differences between those is that when you build a theory based on data explanation, you normally explain the data and you cannot predict anything. And in this case, the theory has a predictive skills, and this is how we can differentiate between better and between different theories, between usefulness of the theory. So this theory, as we shall see, has a lot of predictive skills. And we started with solving Navier-Stokes equation in a rotating coordinate frame, and we didn't even know how wide the applicability of the theory will be. So the motivation of this talk, of course, is put everything together. We know from observations that there are many different observations in different sciences, and atmospheric, oceanic, and planetary sciences. And sometimes they seem to be pulling in different directions, and they seem to be disjointed. And the situation may be sometimes parallel to building the Tower of Babel. It's a lot of chambers, a lot of rooms, and they're not connected and get lost inside this building. And at the end, the whole building becomes destroyed because nobody can attend to it. But apparently, many theories can be put together within this one theory. And in this talk, I will try to present the theory and to go to take you through different chambers and to see that you can go from one to another one. It's all very neatly connected. So I'll tell you what is the outline of this so that you will know where we go. I will start with atmospheric campaigns using commercial aircraft. And they lead to the so-called canonical or Nastrom gauge spectra, which is valid for upper troposphere and lower stratosphere. Then we shall need to discuss the underground physics, background physics for the spectra, because there are many different explanations, and this is not still very clear what's guiding the spectra. The question will be also, do we need the mathematical theory, and what the spectra are good for? Do we need really to pay attention to them or not? And apparently they can be put together using this theory, which is called QNSE. It's quasi-normal scale elimination. So I will go through this theory as brief as I can and show some analytical results. And then we shall derive the spectra from this theory, and apparently the spectra will be very close to this Nussbaum gauge spectra, but they have something which original derivation didn't consider. The next step will show that this spectra which follow from QNSE, they apply not only to atmospheric but also to oceanic turbulence and in very different locations in the ocean. From this, I can extend the theory to show the continuity between mesoscales and submesoscales, at least in oceanic flows. We cannot go too far to the ground because some other effects become important, but we can take it to pretty high, to pretty low, to pretty small scales, or the order of several kilometers. What is even more surprising is that the theory seems to be even applicable to hurricanes and to very interesting planetary phenomenon called superrotation. I will get to that. I'll explain why it's called superrotation. And at the end, we shall see that the famous classical Kolmogorov turbulence, which we know from different applications in mechanical engineering, apparently it works in almost everywhere in atmosphere, ocean, and planetary flows. So this is a really important thing. And the parameter which characterizes Kolmogorov turbulence, called dissipation rate, it's very important for all applications in geophysical fluid dynamics, because it guides not only the flow dynamics, but also when you parameterize it guides the development of subgrid scale and subfilter scale parameterizations. The epsilon is a key parameter. So this is probably one of the most important conclusions. All right, so start with atmospheric sciences. In late 70s and early 80s, there was two extensive campaigns based on commercial aircraft, which were carrying sensors which could measure velocity of the air. And one campaign was organized by American scientists called GASP, Global Atmospheric Sampling Program. And it was summarized in several papers by Nastrom and Gage. This is from 1985, but they have a whole bunch of different papers. And another one was European company, European campaign called Measurements of Ozone Airbus in Service Aircraft, called Mosaic, summarized by Marenko and also Lindberg. And here you can see just how the data was collected. So you can see that the airplane were flying all over the world, here mostly in the northern hemisphere, over land and over water, and some of them were going north-south, but most of it was going in zonal direction.
Of course, how can you test Kolmogorov's theory if you don't fly over Russia?
Kolmogorov theory is universal, Bob. Now, this campaign, you can see the main directions here. They produced thousands of different trajectories. There was different strategy how you can select trajectories. So I will not go through all of this. If you want, you can look into these papers yourself. But they produced this famous Nastrom and Gage spectrum, which is called canonical spectrum. And you can see that mostly it has two branches. Now, this is meridional wind and zonal wind. So this is east-west, and this is north-south. And they're shifted by one decade just for convenience. But if you put them one on the another, they're almost congruent. They're almost the same. So this is the branches. On synoptic scales, synoptic scale for meteorology is not like for oceanography. So it's between 3,000 kilometers to down to 500 kilometers. The slope goes like kh to -3. Kh is a horizontal wave number, so h for horizontal. And on mesoscales from 500 to 10 kilometers, the spectrum goes into Kolmogorov slope, kh to the power of -5/3. All right? So this was now some, well, it was coined like Nastrom and Gage spectra, and they called it the canonical spectra. They did see slight, well, actually it's not slight, but dependence on latitude, but they didn't know how to explain it. So they decided that we can just average it over the latitude, get one line, and call it canonical spectra. And this is how it's used in atmospheric sciences, and everybody refers to this as canonical spectra. Now, here I need to say something important which you need to remember through the rest of the talk. You can measure spectrum along the trajectory. So if you say a trajectory goes zonal direction like this, so if you take velocity in this direction and build one-dimensional spectrum, it will be called a longitudinal spectrum. But we can also take this direction and look at the orthogonal to it velocity at every point. And you can derive the spectrum for this velocity. This will be called transverse spectrum. So they are not the same, and even in isotropic homogeneous turbulence, they are not the same. So we need to remember that there are longitudinal and transverse spectra, and this is what we need to deal with when we deal with spectrum computed in one dimension, in one direction by different tools. So in this case, I double-checked it with the people who build the spectrum. Both spectra are longitudinal spectra, so they're built for the direction in velocity in zonal direction, it's zonal spectrum, and velocity in meridional direction, it's meridional spectrum. So you can see that the longitudinal spectra in both directions are the same, and this is a sign that we have isotropic turbulence. It's turbulence which doesn't depend on the direction, which is very important. On these scales, with large scale forcing in the atmosphere, we're dealing with horizontally isotropic turbulence. It doesn't mean that it's also isotropic in the vertical, but in the horizontal it is. And because of this, it appears like two-dimensional turbulence. And we shall see that it's not exactly two-dimensional turbulence, but in 2 dimensions it is. So this is our spectrum, and now what stands behind the spectrum? So there is a lot of different theories, and I will tell you what was the state of the art until this work. There was an explanation based on Krajcman theory of two-dimensional turbulence, which was extended by Charny in 1971, and he called it geostrophic turbulence. All right, so what it says that we have a forcing in the atmosphere due to baroclinic instability somewhere on large scales. And because of large scales, the flow is quasi-two-dimensional, we have direct entropy cascade. Entropy is the square of vorticity, which gives us this K2 minus 3 spectrum. So this is a vorticity generated spectrum. And then on smaller scales, something happens, and we have Kolmogorov spectrum K2 minus 5/3. The problem with two-dimensional turbulence is that it doesn't give us direct energy cascade. So to explain this thing, somebody by name Doug Lilly assumed that there was forcing on smaller scales by convective storms and other disturbances, and this generates inverse cascade. Energy goes from small to large scales, and it also has the spectrum of K2 minus 5/3. It's a Kolmogorov inverse cascade spectrum. All right, so it was assumed that we have direct entropy cascade here and inverse energy cascade here, and this is how we can explain the spectrum. However, there was a simulation by O'Gorman and Schneider who showed that entropy cascade is not necessary to explain this part. And then Choi and Lindberg shows that there is no explanation of this range, of the spectrum in this range, other than Charny two-dimensionalization, Charny two-dimensional turbulence. So this was kind of a dead end because there was no other series. But then there was another paper by Lovejoy, and he said that he even claims that this spectrum doesn't exist, that it's just due to analysis error. The dynamics of this range was even less clear because nobody observes inverse cascade in this area. And then there was a paper by Eric Lindberg in 1999 in which he used a mathematical tool called structure functions, and he computed the energy cascade direction, and he found that energy goes from large scales to small scales. So it's not even inverse cascade. So what is this? Lindberg assumed that it was stably stratified turbulence, stable stratification, which makes turbulence or flow very anisotropic, and it can facilitate direct cascade in this range. It's 500 kilometers. Of course, there is no vertical scale of 500 kilometers, only horizontal, so the flow is very anisotropic. So you need to account for this discrepancy, otherwise you cannot apply Kolmogorov arguments. Now, on top of everything else, Cho and Lindbergh wrote that Coriolis force may play important role in all these dynamics, but the problem is that to develop their apparatus of structure functions, they needed to use a turbulent energy equation. And the turbulence energy equation, original Navier-Stokes equation has Coriolis term, but when you begin to derive energy equation, Coriolis term cancels out, because Coriolis force doesn't produce work on the flow field. It's a conservative pseudo force, if you want to call it like this. So they didn't have any way to include Coriolis force in the energy transfer analysis. The only way to do it would be through the triple correlation, including pressure. But pressure in physical space is a non-local term, and nobody knows how to compute it. So it was a dead end. So this is where we are. There's still no consensus. There are still many theories, but there is no theory which accounts for everything. All right. Now, how important is explanation of the spectrum? Apparently, it's more than just academic interest, because many models, particularly atmospheric sciences, they're based on models' ability to replicate this canonical spectrum. If you look on many papers, it's always there, and they try to go over it. So the spectrum is used as a tool for model validation and, well, not calibration, but at least validation. And if you also pay attention what they do, people look normally on the slope of the spectrum. They don't even pay attention to the amplitude. It's just too complicated. It's even the slope itself is already a big problem. So the amplitude normally is not paid much attention to. And this is a pity, because the real question is how you can reproduce the amplitude rather than the slope. Even if you look on turbulence theory and Kolmogorov theory, and he did develop k to minus 5/3, but he needed to know what the amplitude of the spectrum is, because without knowing what the spectrum is made of, what parameters come into the spectrum, you cannot come to the minus 5/3 slope. So it's two sides of the same coin, and you cannot just take one of them, because you don't have the whole picture. So the question, is there any connection between model configuration and correctness of the spectrum? This is what we're trying to do here. And are model resolution and subgrid scale parameterization connected to each other, and what they do to the model performance? So then there was even more questions. Lovejoy, actually, they had very good intuition, and they questioned the importance of turbulence and its anisotropization. They said that the different scaling laws in horizontal and vertical may lead to some spurious results, which need to be understood, and there was no tools to do it. Okay, they questioned the attribution of two scaling laws to a dimensional transition between three-dimensional and two-dimensional turbulence. And they concluded the entire mainstream view of atmosphere has fundamentally been colored by the assumption of isotropic turbulence. This is 2009, and there was not much progress since then. There was following up paper by Yana, and he made this convoluted paragraph. You can read it. I don't want to read it. It's like some words are difficult even to pronounce. But at the end, he said that if you want to develop a theory which can describe everything in a consistent way, continuous transition from quasi-geostrophy to non-hydrostatic anelasticity, we may need to go to a use of a theory based on renormalization group that might potentially lead to necessary theoretical breakthrough. But he said, I should not be too speculative. I know this guy, and he's never too speculative, and he published 2 volumes of, on convective turbulence. So he's a very knowledgeable fellow. But now let's go to see what is RNG, randomization group theory is. We go back to the basics, and we recall that turbulence is a commingling of fluctuations of all scales down to the viscous scale, and because of strong nonlinearity, they all talk to each other. They are correlated to each other, and sometimes are very strongly correlated. And because viscosity is very small, the phenomenon of turbulence, you cannot do it in perturbative method because large Reynolds number yields large nonlinear term. You cannot just go and drop nonlinear term from consideration. And nonlinearity is a main culprit of the complexity of Navier-Stokes equation. So there are many different ways to deal with it, but one based on RNG is probably the most promising because it allows to develop some analytical results which were unachievable before. This tool is based on the idea of coarse graining. Okay, what is coarse graining? This is when we take short distance degrees of freedom and try to relate them to long, when we're really interested in long distance behavior. So we want to get rid of small scales and see how they will affect the large scale. So this is like subgrid scale parameterization in simple language. And this problem was applied to problem in critical phenomena, and two guys by name Wilson and Kogut got the Nobel Prize for doing this in critical phenomena. So we shall try to borrow some into theory of turbulence. So this is an example of coarse graining. You take the picture of Mona Lisa, and you begin to coarse grain it, which means that you can reproduce it with larger and larger grains. It's, you know who did it before them? It was Dali. If you go to Dali Museum, you will see he was doing the same thing. And when you get close, you cannot see anything. But when you go far away, then it comes back to a picture. So, so this is very coarse grain, and this is a normal resolution. So you can hardly see anything here, just main features. But so if you develop a subgrid scale parameterization for this kind of process, the areas which have the biggest contrast between black and white will give you the biggest values of subgrid scale parameterization. So your eddy diffusivity will be large here and not very large, for example, here. So this is how coarse graining is working. I probably will not, it's a lot of mathematics here, so I will not go over a lot of it, but I will tell you that QNSC, now we go to quasi-normal scale elimination theory. Conceptually, it's very close to RNG, but it skips some of the intermediate steps because you just cannot do it. It's, I mean, it's called one loop approximation, and there is, we cannot do any more than one loop. But there are some ways to show how it works, and it's very, very involved. All right. But what we need to know is that the theory is applied to the full Navier-Stokes equation. We don't use any quasi-geostrophy. And after we derive, the theory is actually developed to produce analytical expressions for subgrid scale parameterization tools. It's not for the spectrum. It's not only for ocean and atmospheric physics. It's done as a generator of subgrid scale parameterization scheme for large eddy simulations, which can apply anywhere, including the atmospheric flow, but not only. Okay, a byproduct of the theory is our expressions for the spectra, and you can develop three-dimensional, two-dimensional, and one-dimensional spectra, and it's all analytical. So let's go to mathematical formulation. So this is the equation which we solve. It's a normal Navier-Stokes equation. It's in tensorial notation, but it's the same thing. So this is a material derivative of velocity. Alpha is index, can be 1, 2, or 3. This is Coriolis term. F is the Coriolis parameter. This is a viscous term. This is a pressure gradient. And this is a forcing, which is random large scale. It's a delta function, actually, which is supposed to keep the system in steady state. Because if you don't put forcing into it, it will decay. And we have continuity equations, divergence of velocity equal to 0. We do three-dimensional Fourier transform on this thing. Actually, it's not. It's four-dimensional Fourier transform. You have dk is a wave vector. It has three components, and then we also do Fourier transform on time. And as a result, we shall get expression which depends on four-dimensional Fourier vectors. It's all these heads are four-dimensional. It's three components in space and one in time. Now, because it's a spectral representation, Laplacian becomes k-square. So non-local pressure in physical coordinates, in physical space, become local in Fourier space. And this is a big advantage of the theory, because pressure is really a very nasty term. It's very difficult to deal with it. We always have a problem when we deal with it in physical space. But this is our equation in Fourier space. So this is the pressure, and we solved for it explicitly. And you see that it has three components. It has nonlinear part. It's quadratic in velocity. It has a Coriolis part. It should be epsilon, Chevi-Levitt epsilon. But it doesn't have this font, unfortunately. And this is the eddy viscosity part. And in nonlinear dynamics, you actually cannot, they are all of the same order of magnitude. You cannot drop them. If you do drop this and this, you will get geostrophic approximation. And you can happily develop geostrophic balance equation, or balance equation if you want. We normally call this as ageostrophic terms, but we need to know what they are. You can see that viscosity here is quite involved. It has different parts in it, because rotation by itself endows the flow with interesting mixing properties, which becomes anisotropic due to the nature of rotation. And now, interesting thing is that this equation holds for every time scale and every spatial scale. Every spatial scale has its own time scale, and the analysis goes from one scale to another. Okay, so that's very important. Now, on some scales, this term, the Coriolis term, may be more important. On others, this term will be more important. And other terms, this maybe some preference, which means that some scales may be more affected by rotation, some scales are more affected by turbulence, and so on. And by solving this equation for all scales, we can see how this whole spectrum of scales interact with each other. And this is, if you can project a spectrum out of this, then it should have some physical meaning, and we should be able to give it proper interpretation. Now, there are some scales which we need to remember. So this is what we call a Wood scale, L omega. This is rate of dissipation, and this is Coriolis parameter to the power of 1/2. And rotation dominates dynamics on scales bigger than this scale, and turbulence is dominant factor for scales smaller than this. So we have a natural separation between inertial wave dominated or rotation dominated range and the Kolmogorov range. Now, how do we process with how to proceed with the process? We consider all scales in the beginning, and we go to the very small scale, to the molecular scales, and build the Reynolds number around this scale. This Reynolds number will be built on velocity scale, length scale, and viscosity. And because it's all small scales, the Reynolds number is of the order of 1. When it's of the order of 1, we can build iterative process and try to get rid of these very small scales, which are very fast. So we introduce some wave number close to Kolmogorov wave number, and say that all wave numbers larger than this, or scales smaller than this, they are kind of a fluctuating subgrid scales which we want to get rid of, unresolved scale, implicit scales, and all other scales are explicit. And then we derive a process of ensemble averaging over this small shell of the wave numbers. And by doing this, we can get rid of this small shell of wave numbers, but it doesn't come for free. What it does, it produces some corrections to viscosity and diffusivity if you also retain the temperature equation, for example, or salinity equation, or whatever scalar equation. And then you get a new equation which is defined on smaller domain. But in this equation, instead of having molecular viscosity and diffusivity, you now have what we called renormalized viscosity and renormalized diffusivity. This is in physics terms. In normal terms, it's steady viscosity and steady diffusivity. Of course, the advantage of the method is that because of the complexity of the problem, this renormalized viscosity and diffusivity, they may become anisotropic. They may go in different, they may be different in horizontal and vertical direction. And when you have rotation, it's even more subtle because there is also special action of the subgrid scale parameters on vertical velocity by itself. So we have two viscosities which act on all components of the velocity, and two more viscosities, vertical and horizontal, which only act on the vertical component of the viscosity. So we call it componentality. This is something which doesn't exist in stable stratification. So we may wind up developing subgrid scale parameterizations for atmospheric and oceanic flows, which have 4 different viscosities. Nobody is looking forward to this, but it's possible that we cannot do without it. All right? Now, after we completed this step, we see that the equation, Navier-Stokes equation, didn't change functional form. The only thing we changed is viscosity and diffusivity. If you have, or just let's talk about viscosity only. So now we can take another shell. Now we can build another Reynolds number built on the new viscosity, and it will be again of the order of 1. So we can make another step and exclude another, do an ensemble averaging on another shell which is adjacent to the new dissipation cutoff. And by doing this, we shall eliminate more scales. We shall shrink the domain even more. This is what this coarse graining is all about. And our viscosities change a little bit again. So for every delta lambda, for every small shell of modes which are eliminated, we gain delta nu corrections to viscosity and diffusivity. And we can go as far as we want. We can now go to the very large scales, and in this case, we shall have what is called Reynolds Reynolds average Navier-Stokes equation. Or we can stop in the middle and say now we have subgrid scale parameterization for large AD simulation. We eliminated that many scales, and all these scales we can solve explicitly for. Okay, so this is how it works. But we still are dealing with some finite shells, and we don't want to deal with these finite shells because it's difficult to deal with them. So now we take the limit when delta lambda, the length of the shell, go to 0, and this will bring us to differential equation. So we have 4 viscosities, and when we do it, we do this limit for every one of the equations. We have a system of 4 ordinary differential equations, which couples all those viscosities with each other and with flow parameters. And we can solve it, and then it will give us analytical expressions for all viscosities we are dealing with. All right. Before I go there further, we need to introduce this spectral Rossby number, which will in fact separate between turbulent and rotating scales. And I need it here because all the solutions will be function of this Rossby number. So it will give us very convenient way to look what happens. So, so this is analytical results. You can see we have the system of 4 differential equations for viscosities and diffusivities, and 2 more. I mean, this is for viscosities and 2 more for diffusivities. And they all give us nice analytical solutions. Now, rotation has this pesky tendency to change the direction of cascade from direct to inverse. And when we go to inverse cascade, our viscosities become negative. And the model, the theory, doesn't deal with negative viscosity, so we need to stop it at some point. So we only take the approximation of weak rotation, which means that we only take approximation up to the Rossby number, the spectral Rossby number to the power of -2. And but even this gives us very nice results. Now, you may not think that they are nice, but let us see what happens when we compute the correlation function and then the spectra. Before we go further, I told you that we have some, well, I don't know if you want to hear about this. We made comparison between effect of turbulence on rotating flow as opposite to effect of turbulence on stratified flows. And for this case, we have Wood's number, and analog of Wood's number for stratified flow is Osmedov number. So on large scales, I mean on large wave numbers, this is turbulence regime, everything is isotropic and collapses, goes back to Kolmogorov's theory of turbulence. But when you go to the ratio of the order of 10 here, or even for order of 1, you can see that the vertical diffusivity, for example, in stratified flows goes down. The diffusivities in rotating flows, they don't care about rotation that much. Actually, they even increase. But viscosities, they do go to 0. This is where inverse cascade begins. And in stratified flows, we can do integration not in the limit of small stratification, but we can do it for any stratification. And viscosity never goes to 0. That's a difference between rotation and stratification. And in the limit of very strong stratification, we can recover the limit of Osborne-Cox mixing. We can get this equation just from the theory, which is very nice. All right, I can talk more about this, but it's not the center of my point. Now, this is all equations for one-dimensional spectra. You see that E1 is direction in the zonal direction. So it's longitudinal spectrum is E1 of K1. This is transverse spectrum, E1 of K2, and E1 of K3 is transverse, but for longitudinal zonal spectrum as a function of the vertical wave number. So you can have all of them. And now let's see how they compare with the real data. All right, so this is our longitudinal spectrum. And this must be epsilon, and I always have a problem with this. For some reason, they never have this in the font. So this is epsilon to the power of 2/3. And this is Kolmogorov part. And this is Coriolis part. And this is transverse spectrum, again at epsilon. And this is Coriolis part. You see that they have different coefficients. Now, this coefficient, I can write it to you with any degree of precision if you want. But it goes to 0.1. It's a very non-trivial number. And normally, we are used to have something, coefficient of the order of 1. So this people don't think about this thing that's so small. Anyway, I took these two expressions and put them against Nastrom and Gage spectrum. And as you can see, miraculous, it goes right over the data. But I had a problem here because our spectra depends on Coriolis parameters. This guy is averaged, and I don't really know what they plotted here. So I looked at the latitude of 30 degrees gives us the best agreement. But you can tell me it's a fudging, which is fudging. It's a good agreement, but I compare with something which I don't know what it is. So the canonical spectrum is not a canonical spectrum. It's something which actually doesn't exist. So what did Nastrom and Gage think about it? I looked into some other papers, and of course they did see that there is a dependence on Coriolis parameter, on latitude, but they didn't know how to explain it. However, okay, before I go further, I made a presentation of this last year in a conference, and there, Claude Cambeau was in audience, and he's one of the best people in the theory of homogeneous and isotropic turbulence. They just published a second edition of their book. It's about 1,000 pages about all this, everything you wanted to know about this equations, and were afraid to ask. So he liked our agreement so much that he asked me to give him our picture, so he put it in his book. So he published it even before we published it. Anyway, this is what Nastrom and Gage show for latitudinal dependence. You can see that there is some latitudinal spread. But it wasn't clear how they did it and how much they deviated from latitudinal trajectories when the airplane were flying. So we just put 3 different lines from QNSC, and this is what they get for their flights. You can see with different signs. So we pretty much encompass what they measured, and it goes in the right direction. So when f decreases, the slope of the line and the amplitude also decreases. So this is what we get. This is the real data, but I wouldn't call it canonical spectrum. It depends on many things. Now, the easiest way to check the theory is to see if at the equatorial part, the Coriolis branch will disappear completely. So this is what we did. We found the data from this paper by Xu and 2 other people, and this is for scatterometry over the ocean, and you can see this is from their paper. They have 6 different regions, 2 in the mid-latitude north, other 2 in mid-latitude south, and 2 in the equatorial region. And this is the spectral slope they found. So you can see that in mid-latitudes, it steepens up, goes to about 3, but not 3, it's slower than 3. And I can show you why it's slower than 3 a little later. And this is north and south, but at the equatorial region, it's about minus 1.8, 1 point, I don't know. It's getting close to Kolmogorov. It may be a little higher because of different effects. Also, it's not exactly equatorial, but there is no steepening even to the slope of minus 2. So we can see that indeed the equatorial part is different from mid-latitudes. Now, we can go to simulations by Bill Skamarok in 2014. This is his model MPAS, and 3-kilometer global resolution. So this is for troposphere and stratosphere. His data is this lines, and our curve is gray. You can see we have very good agreement throughout all the region. In the troposphere is not as good, but it's some modeling issues as well, and needs to be probably better investigated. What is interesting about our spectrum is that it only depends on Coriolis parameter and nothing else. So from this point of view, it's a generalization of Kolmogorov theory. In Kolmogorov theory, the spectrum depends on rate of dissipation and the wave number. In our theory, when you go to the Coriolis part, it only depends on Coriolis parameter and the wave number. So you would think that it should apply anywhere which is rotating. It doesn't matter is it Earth or ocean or oil or anything else. This is property of universal spectrum. But before we go there, this is very important to stop here, that when you know that your small-scale region is in the Kolmogorov range, you can go and develop subgrid-scale parameterization, which they all depend on epsilon. All right? So this paper by Takahashi, they used state-of-the-art atmospheric models. They computed tropospheric circulation. This is the spectrum they found. And they found that empirically, using many simulations, this is their expression for subgrid scale filter, which is being applied to, it's not Laplacian, but biharmonic friction, so it has different units. We go to our theory and just modify it for biharmonic friction, and this is our expression without any simulation at all. And you can see that they're nearly indistinguishable. This is a little smaller, this is a little higher, but they decay a little faster. I mean, we decay a little faster than they. So the numerically, these numbers will be very close. Of course, nobody tried it, but this is the power of the model. We can produce this kind of expressions, and we know what we are doing. We don't need to run many simulations for this. Now, go back to atmospheric and oceanic turbulence. Even Charny in 71 said it is thought that above theory, theory of geostrophic turbulence, should also apply to the oceans in regions of strong baroclinic excitation, such as the region of the Gulf Stream meanders. But no observations are yet available for comparison, so we cannot say anything. if synoptic branch of the Nastrom gauge spectra is indeed manifestation of geostrophic turbulence, then the applicability to oceanic flows has been hypothesized by other people, even as recent as paper by Hatri of this year. Okay, in QNEC, as I said, our spectrum depends only on epsilon on small scales, F on large scales, and the wave number. And in this sense, it's universal, and it agrees with the Charney assumption that it should apply beyond atmospheric environment. So we can try to validate our expression for oceanic data as well. The only thing that we'll try to do is to avoid the geostrophic approximation, because we know that it may not be in geostrophic balance. We saw in equations that there are other terms which are maybe equally important. So instead of using geostrophic approximation, we relied on ADCP, on acoustic Doppler current profilers, which gave us the currents. And now we used 3 different locations. One is the vicinity of the Gulf Stream, and the data was produced by the container motor vessel CMV Oleander. That's number 1, and I have quite a lot of comparison with them. Another one is Northwest Pacific along the 137-degree east meridian. This is from CHU data, and ADCP was running by Japan Meteorological Society. Bo gave me, along with Kurosho region, he gave me 3 others. And then in the beginning, I didn't want to use it because they were not forced the same clear way as Kurosho. But then I could use them, and you will see what happens with this. And the third area is Antarctic, is ACC, and there ADCP was collected by U.S. Antarctic Research Supply Vessel, ARSV, by name Lawrence Gould. And the ship was going south of the Drake Passage twice a month. Well, you can see the data is from Rocha et al. So let's start with Oleander. This is how it was going. This is the trajectory of the ship, mean trajectory. And they plotted mean current and velocity ellipses. So in the area of the Gulf Stream, there is anisotropy introduced by the current itself, but you go away from the current and it's becoming more and more isotropic. It's plotted every 20 kilometers. This is 30-meter depth. All right. And they measured 2 spectra given by 2 lines here. It's longitudinal spectra. And our line is red, okay? And you see that our line goes right over their data when we took theta equal to 37 degrees north, and epsilon was at this number. And this epsilon, I must tell you, it's a quite a realistic number for oceanic dissipation rate. Now, this was taken over a very long time, so it has seasonal variability built on, so it integrates between winter and summer when we know that it's not exactly the same. So now we have more data, so we can see if the theory, how it responds to different levels of turbulence. But again, I'm telling you that this line is following from analytical theory with no any empirical constants. The only thing which you can play with is theta and epsilon. And of course, they need to be realistic, and of course, they are realistic. This is what it is. This is 37 degrees is here. If you go a little down, it will go to 35 maybe, and the line will go a little bit down, but it will not differ that much.
So Boris, explain how that spectrum was calculated.
Spectrum of us or theirs?
Theirs.
Well, they computed the velocity field. Well, the things that I remember how they did it. I think they straightened it out along the line.
Okay, so the line is
right.
Cuts through a lot of different latitudes. So
right, but since once you have a line, you can compute the spectrum. But I may be fantasizing. I'm not sure how they did it. I will not tell you what I don't know.
okay.
All right, I just used their line and I plotted our line over their line. That's all.
I'm confused how, if the line cuts through a lot of different latitudes, how do you get the latitudinal dependence on the spectrum?
Well, in this area, I was thinking about it, but you can use F-plane. It's not a beta plane yet. And in F-plane, your F is constant. And you can get away with this. Now, there was another paper by Oliver Buller in 2017 who thought about anisotropization introduced by the Gulf Stream. So the ellipses are not exactly isotropic. So he introduced a different way of computing spectra and rotating the spectra, and he produced his spectra in this paper. So Buller spectra are given by solid line. This is longitudinal spectrum, and this is transverse spectrum. And this is, again, for Oleander, but I think it was for a different time period. And our lines are given by this dashed lines. This is transverse, and this is longitudinal. Now, Buller, again, didn't differentiate between summer and winter, so he put everything together. And we don't really know what it does to the spectrum. I didn't know how to deal with it. So if you take the winter value, which is a little larger for epsilon, then you get a better agreement on the small scales, but not as good in this range. But if you take the summer value, which is a little smaller, then you have a better agreement for mesoscales, but not as well in, you call it sub-mesoscales. But we cannot do any better because they didn't differentiate between them, so I don't really know how to compare them. So this is why we got two different lines. But there was another campaign, another Oleander campaign. This is one which Buller worked with, and another one called LATMIX, and this is in the paper by Callis. So LATMIX was measuring also not far away from Oleander, so you have LATMIX in the winter, in summer, and Oleander, and they tried to see to distinguish between winter and summer values. So this is easier because epsilon is better determined. So we take Oleander winter data for 50-meter depths and summer data for 50-meter depths. They didn't give us the same kind of spectrum. So for winter, they did give us longitudinal and transverse, but for summer, they only gave us kinetic energy. So this is what I had. You see again that we have pretty good agreement with them, okay, in both cases. This is our data. I mean, this is QNSC, and this is their data. And at the very end, they claimed that the physics become internal wave spectrum by Garrett and Munk, and this is Garrett and Munk line is. But as you can see, our theory goes right over Garrett and Munk. Without any tuning, I just plotted as it was, and we even recovered this. This is really amazing that this theory can do so much in such a simple set of equations. All right, so this is what Oleander gives us. Now, this is LATMIX. This 20-meter depth for winter and for summer. Their data is thin lines, again, longitudinal and transverse, and this is kinetic energy. And our theory is thick lines of the same color. So for winter, we go right over their data. You can see we recover it on all scales. And in summertime, we again recover Garrett and Munk spectrum. So this is a very, very pleasant surprise for us because we didn't think that we can do even this. But the agreement here is really very good. Now, let's go to the next area. It's Northwest Pacific. And this is ADCP data which was collected by Japan Meteorological Society and was processed by Chu and his team in Hawaii in 2017. So they have 4 different regions. One is near Kuroshio, and they have this one and this one and this one. So this Kuroshio, I give you the latitude range, belt, then subtropical countercurrents, STCC. You can see the belt of latitudes, north equatorial current and north equatorial countercurrent. These things, they're not even forced at large scale. So in the beginning, I only wanted to compare here when we have Kuroshio, which is similar to the Gulf Stream. But since he gave me all the data, I thought, I can just look what happens in other places. It should be a place where the theory doesn't work, right? So this is what happened. I plotted, and you can see There is agreement, good agreement in all 4 areas. It didn't work in the beginning when I didn't adjust the Coriolis parameter to the proper latitude of the belt. But the moment I put the correct latitudes in the equations, I have a very nice agreement throughout all scales, at least mesoscales, also partially sub-mesoscales, and the agreement is good. Now, you can tell me that the spectra here are not -3. The point is that you cannot compute the spectrum for the entire line. It's wrong, because we have 2 different regions. We have Kolmogorov region, and we have -3 rotation dominated region. And if you put them all together, I don't know what slope you will get. It will not be Kolmogorov, and it will not be -3. It will be something in the middle. So when you plot the spectra, you really need to know what region you are studying. And without knowing the theory, you don't know how to even process, how to approach it. And people publish all kinds of spectrum and slopes, and it's just a big mess. So having analytical theory in this case is really useful. Now, the next one is the Drake passage. So this is ADCP data collection, and this is simulation with 1/48-degree MIT GCM. And this nice thing we can compare with each other. Okay, so this is comparison is north of the polar front. All right, the data is here, the solid lines, and the model is here, the dashed line. You can see that again the agreement is really good in the entire range of the scales. Now, if you look on the comparison with the model, our lines are the same, but the model doesn't have enough energy on small scales. So it looks like MIT GCM really needs to work on their subgrid scale parameterization, because they seem to be killing kinetic energy on small scales. And again, without having analytical theory, you will not know what to compare. You will not know how to get to these conclusions. So this is really the power of having analytical theories for this kind of simulations. Well, I will skip over this. Now, from method to sub-mesoscales, because I'm running way over time. So there was a recent paper by Archer in which he used high-frequency radars to try to see analogy, kinematic analogy between strong boundary currents in Florida and East Australian shelf. So this is an area which you could study with high-frequency radars. And the advantage of radar is that it doesn't require geostrophic approximation. It just uses velocity as it is with high-resolution velocity. And of course, the area is small. So what we can do is to try to connect sub-mesoscale results with mesoscale results from the theory and see if we can achieve some continuity between the two. So this is what we get. These lines are theoretical lines which I took from this area, just approximately assuming that I know the theta and I more or less know the epsilon. And this is the data from high-frequency radar. Okay, they cover much smaller area, but you can see that there is indeed a very strong hint on continuity between mesoscales and sub-mesoscales. And this is just first paper just published this year. There is another one by 2 Korean guys, which gives more or less the same agreement. And this is very new research. More needs to be done, but it gives us a way how we can go, how we can look for continuity between different descriptions of the ocean. And I think it has a great future just because even in the initial stages we have such a good agreement already. Now, I'll take you to a completely different area. It's hurricanes. Hurricane is a big vortex, and some brave people take airplanes and fly through it. And on the way, they can measure the spectrum. Okay, and there is a recent paper by Vonich and Hakim, 2018. They say it's all new data. It's the first time I saw it, and the first thing which attracted my attention was that it has the Kolmogorov part and the steepening to K2 -3. How come? What is it doing there? It's not supposed to be there. The scale is too small. It's not real atmospheric turbulence, so why does it go into this regime? Well, that's a good question. They didn't answer it. They didn't even ask it. But let us look on the mean flow equation in polar coordinate. In mean flow equation, you have this extra term, u square over r, but I took u out, and we have u over r plus f. F is a Coriolis, and this is u. So if you want, you can consider u over r plus f as an effective Coriolis parameter. All right? And if this u over r, and u may be very large in the hurricane, if this exceeds f, then this whole thing will be driven by its own rotation rather than Coriolis. And in this case, you go back to our system of equation, and lo and behold, we have -3 spectrum again. But instead of f squared k to -3, we now have u over r squared k to -3. Right? I didn't make the comparison. I should do it. I didn't do it. But look what happens here. This is by categories. Category 5 is the strongest hurricane, and it has the biggest tilting toward k to -3. The tropical storm in category 1 is the weakest, and they don't have any tilting. They just go like Kolmogorov all the way through. So first of all, it's amazing that Kolmogorov turbulence holds even for hurricanes, because this is clearly not standard Kolmogorov turbulence. This is something else. And second, it seems to be even agreeing with our theory that if your Coriolis parameter is small, then, and they're both small actually, then it's pure Kolmogorov turbulence and nothing else.
So how do you calculate that wave number spectrum?
That wave number spectrum? The same way as you do spectrum in flying airplanes. There are many ways to do it. You can rotate it north-south, I mean, in zonal and meridional direction, or you can just go along F itself, on the F plane.
Right, but you have one event inside a larger field, and how that one event projects onto the wave number space is going to determine the spectrum, regardless of
It's not one event. It's hundreds of events. It's many different flights they combine together to compute the spectrum. It's many realizations.
Hurricanes or one hurricane?
Many hurricanes, or many flights in one hurricane.
But you still have the structure, the physical structure of the process that you calculate a spectrum for has, in essence, a delta function in the middle of it, you know, a hurricane. And then the rest of the field is, you know, not much. And so how that spatial structure projects onto the wave number plane is going to determine your spectrum.
Well, what you need to do is in statistical analysis, you need to collect enough realizations, all right? So you can fly through the same.
What you actually have to have, I think, is maybe 10 different hurricanes at once, and you fly through all of them, and then you can calculate the wave number spectrum.
Why do you need to tell them 10 at once? Why cannot you go one and then another one and then another one?
I mean, any event will have a certain Fourier representation to it. But when you calculate a spectrum and you try to relate that to some statistics, you basically have 2 degrees of freedom in that calculation.
Well, I will not go through. I cannot tell you exactly how it's done.
Right.
It's described in this paper, okay? I just wanted to show this, and there is another conclusion here that when rotation is small, by the way, this is your geostrophic approximation, and when this term is small and you only have this and this balance, it's called cyclostrophic balance, okay? So we can have, sometimes we can have a cyclostrophic balance on the whole planet if F is small. And in this case, the spectrum is supposed to be Kolmogorov, purely Kolmogorov.
Okay.
All right, so from here we go to the superrotation. This is a very interesting phenomenon which is observed on slow rotation planets such as Venus. Titan is not a planet, it's the biggest satellite of Saturn, but it also has a slow rotation. And look what they do. The velocity on the ground, Venus is a very funny planet. 1 day on Venus is longer than 1 year It takes longer for Venus to do one revolution around itself than around the sun. Okay, and Venus is a very strange planet. It's the only planet in the solar system which rotates in opposite direction and goes clockwise. All right, but what happens here, you have very slow velocity near the ground, but when you go to the altitude of 60, 80, 100 kilometers, like here, 50, 60, 70, the velocity becomes very large, 80, 100 meters per second. And how it's coming to such a large value from a small rotation near the ground is a good question, and it's not answered yet. Okay, but what is important here is that f is very small. Based on what we see before, we could expect that the Kolmogorov spectrum extends throughout all scales on Venus and Titan to almost to the scales, large scale where the baroclinic instability takes place. So there is no measurements, of course, and particularly for Titan. Venus is very difficult to measure. But there are simulations. My colleague Peter Reed in Oxford, this is the paper is just in press in Quarterly Journal of Royal Meteorological Society. And omega prime is a ratio of actual rotation of the simulated planet to rotation of Earth. So you can see that this is 1/8 of Earth's rotation, and this is 1/16 of the Earth's rotation. And this is the spectra they plotted. You see, this is Kolmogorov spectrum, and this is what they found. And it's really Kolmogorov spectrum almost to the very large scales. Of course, you have other things, and so they have some jets, and they need to work on it. But the tendency is to develop a Kolmogorov spectrum. I also have results from very high resolution simulation from a Japanese group, and they show the same result. So in a sense, the superrotating atmosphere of Venus and Titan are in the regime of cyclostrophic balance, not just trophic, but cyclostrophic balance. And you can draw a connection, a similarity between the hurricane on Earth and superrotating atmosphere on this slow rotating planets, which is amazing. And this is a conclusion which, of course, we didn't even think about when we developed the QNSE equations. So I told you we have a theory for which we found a lot of data. We even developed a new criterion for superrotation, that epsilon, the rate of small-scale dissipation divided by omega cube, which is angular velocity of rotation of the planet, times r squared, the radius of the planet, should be bigger than 0.1. And this should be very general criterion which should apply to even to exoplanet, extrasolar planet. And the beauty of this criterion is that it relates the turbulence parameter epsilon to planetary parameters. And as I told you, this epsilon has traditionally been ignored in atmospheric, oceanic, and planetary science. So we're trying to put it back, that's all. So now we have conclusions, a little over time, but I hope you enjoyed the information. So rotation seems to be of paramount importance for planetary circulations. We can explain Nastrom gauge spectra within analytical theory of turbulence. Okay, this theory, QNSE, uses Navier-Stokes equation in rotating frames and uses no approximations. It utilizes the concept of anisotropic turbulence. Well, the results are in good agreement with observational data sets in many different environments. It provides expression for sub-filter scale, subgrid scale parameterization, which can be used in numerical schemes, in schemes of atmospheric and oceanic circulations altogether. We have analytical expression for spectra, as you saw, and also structure functions. And we account for latitudinal dependence, which is very important. Of course, physics is important. And the physics follows from physics and mathematics here are in big harmony. The physics is in Navier-Stokes equations, and to get it from the Navier-Stokes equation, you need to apply some mathematical tools to distill it out. QNSE provides guidelines for understanding of transition between mesoscale and sub-mesoscales. both in qualitative and quantitative sense. Now, I didn't say anything about the equatorial phenomena. If you look on the energy, you integrate the equation, your energy will be going like F squared times scale square as well, which means that in mid-latitude, the total kinetic energy is pretty much hardwired to the location. So if you want to look at a climate, this is your climate. It's average, something average which is fixed in time. The only place where this limitation doesn't work is the equatorial part. And this is why equatorial region is so important, and all the important climate phenomena take place on the equator. And this is El Nino, this is Madden-Julian oscillation, this is quasi-biennial oscillation, and you have a bunch of other instabilities. They all take place in the equatorial region because rotation cannot do much, cannot restrain it that much. And this is very important. Now, another thing which should go to theoretical fluid dynamics, that rotating turbulence reveals properties of flow with a dimension bigger than 2 but smaller than 3, rather than complete two-dimensionalization. So I would even go as far today as ask to replace the notion of geostrophic turbulence by turbulence in compactified dimension space, in dimension between 2 and 3. In this dimension, you can have dual cascade, you can have direct and inverse cascade at the same time. And we don't have these restrictions imposed by geostrophic turbulence and requirement for geostrophic balance or any balance, which otherwise you need to use in conventional and traditional approximation and the traditional approach to geophysical fluid dynamics. All right? Now, the Kolmogorov cascade, as you could see, is omnipresent. You find it even in situations where you don't expect to find it. And this is a little provocative, but I think it actually makes sense that we need to reassess our over-reliance upon the approximation of geostrophic turbulence and the assumption of complete two-dimensionalization of planetary circulations, not only on Earth, but on other planets as well, even planets which rotate very fast. So, one more thing. I was talking about slow rotation here and the super rotation, but I also dealt with fast rotation. And this is the result of dealing with fast rotation. We have a book on zonal jets coming in Cambridge University Press at the end of this year. And it has a lot of information on zonal jets everywhere in the atmosphere and ocean and giant planets and the physics and theory and everything. So I can just recommend if somebody wants to know a lot about the jets, or anything actually, a lot or not a lot, they can read this book. This book is quite unique. There's no other book on zonal jets. Now I'm done. Well, any questions?
I'd like to ask a dumb question.
There's no dumb questions. Somebody